Welcome. We will have lecture 16 for the course corrosion failures and analysis. And topic what we discuss, we continue our discussion on dealloying and or selective leaching. Now, in the last lecture, at the end of last lecture, we have shown some examples of dealloying, and while analyzing the mechanism, we said that there could be possibility of both mechanisms are working. So, in one case first few layers zinc dissolves in case of dezincification leaving copper, and then finally, it is basically the second mechanism which becomes predominating mechanism or dominating mechanism, where both dissolves either in case of copper and zinc both dissolve, in case of silver and zinc both dissolve, and later on zinc stays back, silver deposits back in case of copper silver zinc alloy, or copper deposits back in case of copper zinc alloy. So, that way we develop that nice porous structure on the surface, and where ligaments are either copper in case of copper zinc, and in case of silver zinc it is a silver. But remember that it may not be possible to get to 100% copper or 100% zinc. For that reason, we have to also have some special requirements to be met in the solution, but definitely we would get close to around 90 to 97% purity of the noble element in that particular couple. So, it might also happen in case of multi-component systems. Remember, in case of multi-component system, this is also possible. Okay. For example, we have seen in our work that multi-component zirconium based alloys, we got to see that when there was palladium or platinum, we did see that platinum and palladium are actually enriching on the surface, leaving copper zinc behind. Okay. In case of zirconium copper system, copper enrichment might be possible, leaving the zirconium behind. Okay. So, I will show you those data in a little while. But coming back to the mechanism part, mechanism of dealloying, it has a strong, and there are two processes. One is noble metal stays back, and active metal dissolves, and second part is both noble and active elements or metal dissolve, and noble metal ion redeposits back, redeposit back. So, these are the two processes, and those two processes can go on parallelly. Now, coming to a mechanism, so it has a strong correlation that even if we try to see that noble metal stays back or noble metal dissolves, it has a strong correlation with pore bay diagram. Pore bay diagram, fine. Now, if we try to look at the pore bay diagram in case of silver copper system, because we have done that study in our lab. So, we will talk about silver zinc system, and let us see whether we can have this situation that silver indeed would stay back or would deposits back silver ion if it is forming on the surface, and zinc would dissolves. Okay. So, in order to do that, let us go to the PPT again. If I see this PPT, so this particular PPT we have seen in the last lecture. If we see that, we could see that we started with silver 50, zinc 50, that was the alloy powder we took, and then finally we got 100% silver. Over the entire powder, the entire zinc 50% zinc content has dissolved, okay, in the form of ions in the solution, and that solution was 2 normal HCl and 0.005 molar AgNO3. So, AgNO3 was added, you know, in the beginning when we were doing this particular operation at 2 normal HCl, 100% silver was not obtained. There were little bit of zinc left out. Some places we could see around 2% zinc, some cases we could see 1%, some cases we could see 3% zinc were left out, even after we went up to 48 hours of dealloying in that same solution. Fine. So, then we thought that we should add silver nitrate solution, which will increase the silver activity, silver ion activity in the solution, which will allow zinc to further come out and everything would become pure silver, okay, but still it is acidic. This is important information, remember this is very, very important information, still it is acidic, and that is what would see that its correlation with pore bed diagram of silver and zinc. Fine. So, let us see the next page. Okay. So, now this page let us look at. Okay. So, now before doing dealloying, actually we did free corrosion dealloying. Free corrosion dealloying is basically we have made that solution, and in that solution we dip the powder, okay, and we have churned it little bit, because if the powder is accumulates at the bottom of the beaker, there could be possible that the outer layer of that accumulated powder or the heap of powder would get dealloyed, but the center part of the powder heap may not get dealloyed. So, that is what we did. We actually churned it. How did we churn? We put it on a magnetic platform, magnetic stirrer. Okay. So, that magnetic stirrer would give us a kind of churning effect, okay, and we had put a small iron that magnet. I think just a minute, let me just recall. No, it was basically fish bubble we had used. You know, if you see aquarium, we have a bubbler used. There is a small pump which is used, which actually gives bubble formation, which allows bubble formation in the water, and that is what it looks beautiful in the aquarium. Okay, fish aquarium, small household fish aquarium. There we have a bubbler, we call it bubbler, fish bubbler, where bubble forms by sending air into the solution. So, that leaves the bubble, and that bubble formation will have a little bit of churning in the solution. Okay. So, that is what we did, and that is what we did, and we saw result. And in the beginning we saw that silver enrichment is taking place. In order to understand that, what we did, we measured the OCP, open circuit potential. If we go back to our earlier lectures, okay, so where electrochemistry has been talked about, the electrochemistry related to corrosion has been talked about, you would see that OCP is open circuit potential. When you take a metal, you dip in an electrolyte, you measure the potential of that electrolyte with time. At some point of time, it will stabilize, and that time you are actually not sending any current from outside. Okay. So, this is open circuit condition, circuit is not closed in that particular potentiostat. So, that potential we call it open circuit potential. So, that is what it is, OCP. Okay. Now, in HCl, 2 normal HCl, we took another composition. This is the composition we took, silver 25, zinc 75, still we got 100% silver. So, this is a silver a zinc enriched alloy, but still we got 100% silver nanoporous particles, those each particle became nanoporous. So, their entire zinc actually goes out into the solution in the form of ions. So, we measured the OCP of those powders. How did we do it? What we did, we made a palette out of it. That powder, we pressed it, mechanically pressed it, and we made a palette. So, that palette looked like this. So, this is this alloy powder palette, and then this disc was placed in potentiostat to measure the OCP. Okay. Even though there are porosity, but still we could have that OCP measurement, and even after 3500 seconds, okay, more than close to around 1 hour. Okay. So, that even after that we could see it is a very stable OCP. Okay. So, that means OCP is with respect to standard hydrogen electrode. We initially measured in terms of with reference to standard calomel electrode, and then converted that potential into standard hydrogen electrode. Okay. I hope you will be able to know what is the conversion. Let us say if it is a standard calomel electrode and if it is a standard hydrogen electrode, this is standard calomel electrode, okay, standard hydrogen electrode, and standard hydrogen electrode 0 point is here, and with reference to standard hydrogen electrode, the standard calomel electrode, the potential it is basically around 0.241 volt. Okay. So, this voltage in standard calomel electrode is measured with reference to standard hydrogen electrode. So, when we measure some voltage with respect to standard calomel electrode, this voltage becomes 0, the reference value would become this. Okay. So, that is what, if some value becomes, let us say this potential is minus 0.441 volt. So, that means that potential if you measure with reference to standard hydrogen electrode, so you just corresponding point. So, this would become minus 0.241. Okay. Just a minute, let me see, this is 41, no, it would become 200, okay, because the entire gap is, this gap would be 0.441 minus plus 0.241, it becomes minus 200, sorry, this is not the potential, minus 200, okay, and then you have actually consumed this much of potential. So, this is from here, this gap is 400 minus 0.441 volt, this gap is minus 0.441, because with respect to saturated calomel electrode, this becomes my reference potential. And now, with reference to standard hydrogen electrode, if we would like to measure, we know already to reach to that 0 reference potential with respect to standard calomel electrode is actually plus 0.241 volt with reference to standard hydrogen electrode. So, the remaining potential would be 200 minus 200 volt. So, if you add these two part, so then it would become again it would become minus 0.441. So, in terms of with reference to if I try to measure this particular potential with reference to standard calomel electrode, so that potential, if it is E, let us say this potential is E. So, this E would be in terms of standard calomel electrode, it would be minus 0.441 volt, but if we try to measure with respect to standard hydrogen electrode, it would become minus 0.200 volt. Okay. So, that is the way we can convert one from one scale to another. Okay. So, now coming to here, so we measured that particular potential of that palette with reference to standard calomel electrode, and then we converted everything in terms of standard hydrogen electrode. Why we had to convert everything? Because in the book the Pourbaix diagram is measured with reference to standard hydrogen electrode. Okay. So, now this is the potential of the alloy, this is the potential of the alloy in that particular solution with that pH. Okay. Now, what we did, we had taken Pourbaix diagram from the standard books, and that Pourbaix diagram, in that silver Pourbaix diagram and in zinc Pourbaix diagram, we actually plotted that potential. Okay. And we also know the pH of the solution what we are using, which is 2 normal HCl, and you could see that this potential, which is around -2 to -4 volt, around that volt. So, that is coming here. Okay. Now, this is also coming in the pH in the zinc Pourbaix diagram here. So, this is zinc Pourbaix diagram, this is silver Pourbaix diagram. Now, if I see the potential here, okay, that OCP value, that is the potential of that particular alloy, that potential and the pH also we have measured. So, pH is around 0.2 is the pH of that solution. Okay. And with that we have done from the by measuring it with the help of a pH meter. So, now this is crossing here, this arrow, if you see this arrow, it is crossing here, and now where it crosses, it is crossing here, that crossing point lies in the silver zone in case of Pourbaix diagram. So, in case of zinc Pourbaix diagram, silver Pourbaix diagram. So, if I try to draw the left part of it, it is here. So, then it is, so this is Ag, this is Ag plus, this is Ag2O, fine. Now, we are having it here at this portion, which is the silver zone, which is immunity zone. So, now if we have that particular, for example, if we take a silver block, if you dip it in acid with this condition, if the potential you have silver potential you have taken forcefully to this particular potential minus 0.2 volt with reference to standard hydrogen electrode, it will lie here. So, silver will not dissolve, it will remain immune. Now, the alloy experience the same potential, and that potential with reference to the zinc Pourbaix diagram, let us see where it lies. So, here it lies. So, this is the OCP of that potential or the free potential of that particular alloy, silver 25, zinc 75, and it is in weight percent, remember, and the pH we know, which is 0.2, and that point is lying here. Okay. So, that is, let us see where it is lying. It is lying in the zinc plus ion region, and this zone is called corrosion zone, fine. So, now this particular point, if we take this alloy to 0.2 normal HCl, and if we see their position, relative position with reference to the pH and potential of that particular alloy, it is lying in the corrosion zone of zinc and it is lying in the immune zone of silver. So, that means silver should not dissolve and zinc should dissolve. Okay. So, that is what zinc dissolves, silver stays back, but finally of course, the actual mechanism starts happening where both dissolves and immediately silver deposits back. It is basically a kind of monolayer ion formation or few layers of that ions having silver ion as well as zinc ion, but immediately silver deposits back and zinc stays back in the solution. But that staying back also has a relation that it is actually that potential is always lying in the corrosion zone of zinc Pourbaix diagram, but silver one is lying in the immune zone of Pourbaix diagram. So, that is the beautiful relation. Okay. Now, another important thing is, for example, the first monolayer is having, let us say this is the first layer and the another layer is forming. So, this is the first layer that is having silver enrichment, Now, once the silver enrichment happens, one might have a query that this alloy initially it was silver is 25%. Now, once the first set of dealloying happens, the first monolayer dealloying happens, it is becoming enriching with silver. So, that means this concentration might go to Ag on the first monolayer, Ag let us say it becomes 70, zinc 30. So, that might happen. Now, if silver enriches, the alloy itself become nobler. Okay. So, how to understand that which one is noble, which one is active? The noble means its potential, reduction potential goes up. So, that means this OCP will go up. Okay. So, now OCP go up means it will try to reach to this level. As it is going towards closer to that particular situation that silver is enriching. Now, interesting point is, even if OCP goes out of that section, then the second mechanism would still be there, because silver has a higher reduction ability in compared to zinc when we have both. Okay. So, that means silver deposits back continuously and zinc continuously comes out in the form of ions. So, that means you can see that there is a strong relation for the dealloying with the Pourbaix diagram of both the elements, that is noble and active elements, and that is very clear that you have to just do that experiment. If you take any alloy system where one is noble, one is active, okay, you take Pourbaix diagram of both the elements, okay, and now you measure the OCP of that particular alloy, that OCP and also the pH of that solution where you are dipping, and that time if you see that cross section point, the pH and potential cross section point, if it is lying in, you will see that the element which goes out in the solution, that particular cross section point, the pH and potential would lie in that active zone or the corrosion zone of active element, and it will lie in the immune zone of the noble element. This particular phenomena will be true. Okay. Now, coming to the point that if somehow we change the pH, what would happen? Okay. The potential, if we change the pH, let us say we have made pH to a very large level and that OCP we have measured. This particular alloy, same we have made a palette and then we have dipped it in NaOH solution, okay, and which was 1 molar NaOH. If you see, this is the 1 molar NaOH we have dipped, you can say this is 1 molar NaOH, and we saw that the that OCP value of that particular alloy is around this particular potential, okay, around minus 1 volt with reference to standard hydrogen electrode. And we have also measured the pH of 1 molar NaOH with the help of a pH meter, and that pH came out to be 11.8. So, 11.8. Now, what we did, we tried to again plot that OCP which is minus 1 volt in NaOH of that alloy and the pH of that NaOH solution, and we could see. So, in case of silver Pourbaix diagram, it is lying in the silver zone, but in case of zinc Pourbaix diagram, it is lying in the zinc oxide zone. Okay. So, that means we should expect that silver would stay back and zinc oxide should form, fine. Now, when you have a solution, this is a solution, in that solution initially let us say this is silver zinc alloy, okay. From that zinc is dissolving. So, this is full of zinc plus plus ions, and it is becoming interconnected silver. Okay. Now, this zinc ion, we thought that let us recover that zinc ion, okay, whether it is possible in the form of some useful product. Now, we took the powder out, or rather filtered it out, and that we took solution, and that solution now you do not have any silver, the silver particle which is porous, nanoporous silver particle, it is only zinc plus plus. And then what we did, we put NaOH solution, okay, till it reaches to the level of pH of 11.8, and interestingly we got zinc oxide nanoparticle. Okay, zinc oxide nanoparticle. Let us see whether zinc oxide nanoparticle has been obtained. You see this. Okay. Now, there we, after we have done the dealloying part, we took the nanoporous silver particles out, we took the solution, remaining solution, we started mixing NaOH solution in that. So, first NaOH will neutralize HCl, and then after that we keep on adding NaOH, so that the pH level goes to 11.8, and then we could see that zinc oxide started forming. So, these are all zinc oxide nanoparticles. The particle size is of the order of around 60 to 54 to 60 nanometer. So, those are pure zinc oxide nanoparticles. So, what I mean to say that through that relation with the Pourbaix diagram. So, now you must have wondered that why we are trying to learn Pourbaix diagram in electrochemistry. The Pourbaix diagram can explain many of the phenomena, the way it has explained the preferential dissolution of zinc and making of silver nanoporous particles, and then finally we could recover that zinc in the form of zinc oxide, and zinc oxide has got many uses. Okay. So, that part is different, but at least we could recover those zinc ions, otherwise you just throw it out. Okay. So, that is what I am telling. This Pourbaix diagram, learning Pourbaix diagram is very, very important while learning any of the corrosion phenomena that can relate the practical situations. Okay. We will talk about this Pourbaix diagram, influence of Pourbaix diagram as the time passes on, and as we see many other examples like this. Okay. So, let us stop here, and next lecture we will touch upon this particular aspect. We will take some of more practical examples and try to see what are the protection routes of dealloying. Now, coming to another aspects, if you could recall that while talking about galvanic corrosion, we said that galvanic corrosion sometimes it becomes good aspects, it is not always bad. We could see two examples, one is sacrificial protection, okay, where the zinc magnesium dissolve and it protects the steel. Okay. And another example we show dry cell battery. In case of dry cell battery, zinc casing dissolves and electrocathode reactions happens on the center graphite or carbon electrode, and zinc dissolution happens around that zinc casing, and we get some potential output which is 1.1 volt, and those are the dry cells. So, those are actually examples of advantage of galvanic effect, which is the advantage of corrosion. Now, here also you would see in the next class also would see that dealloying is a kind of tool to prepare many exotic porous materials. We could make porous catalyst by using this dealloying process. Okay. So, the corrosion phenomena is not all the time bad, that can be useful for making some useful product. Okay. So, that is what I mean, that corrosion is not bad all the time. This is a kind of eye opener that it can be useful in many instances. We will also look at those issues as the time passes on, as we go into go and learn this subject more and more. Okay. So, let us stop here. Thank you.